Okay, sure. All right, so those of you who are here, I want to make this clear. Patricia just wrote this up. Okay, her office hour tomorrow from 3 to 5 will be a virtual office hour. In her virtual office, which can be your virtual office as well, through the chat function in B courses. Let me just ask you guys this, and keep in mind that we're memorializing all of this through my pickup over here. What do you think so far of B courses? Is it useful? Do you like it? You like it better than B space. Okay. But you're an outspoken minority, which is very important. That actually means you're good. Yes? Like it? You like it? I think it does, but the one thing I'm sort of unhappy with about it is that in B space, you could add anyone to the class. They didn't even need to have a berkeley.edu address. So I added, for example, the other Bernstein who's teaching in the department, Adam Bernstein, I added him to the list so that he could see what a 290 class looked like, and he could get the same access. So in contrast, B courses is protecting your tuition dollar. Only you must have a berkeley.edu address or it won't let you add it. So you can't add somebody even as an observer if they have like an llnl.gov address. It won't do it. It bounces them. I tried to add you, Josh, as your Gmail account. Yeah, it wouldn't let me. Gmail was not acceptable. So we still have 2 minutes. And I think there's still bread here. There's a little bit left here. So come on up and grab bread. You're going to need all the sustenance you can get because today we're going weird. Okay? Quantum mechanics. It is, yeah, everyone knows you need carbohydrates to deal with weirdness. Okay? Well, there's strangeness. I don't know, is there weirdness too? Strangeness, yeah. We're not going strange. Nuclear physics hardly ever goes strange, at least low-energy nuclear. Neither is it charming, nor does it have any truth or beauty. It's all just up and down. But definitely it is, this part is definitely strange. So we are, but fortunately we believe we've run out of families. It appears that there's only 3 families of particles. Three families of quarks, 3 families of leptons. We're pretty certain about that. It's pretty kind of depressing. The standard model is really working. Okay, so the truth is that people mistakenly thought that if you have neutrino mass that's a problem with the standard model. No, it's just a feature. It's fine. Yeah, maybe. So we've got the third. There you go. People could have religious connotations to this. All right, it's 12:10. And I will start the lecture. So today we start another one of these little mini chunks in the course. This one is on quantum mechanics. Without any doubt, in my opinion, the most fun aspect of nuclear physics is quantum mechanics, but it is weird, okay? In much the same way that relativity is a bit bizarre, okay, and you have to accept the fact that time gets dilated and lengths get contracted. In quantum mechanics, you have to give up time-honored ideas like you can know where something is, okay, with great and perfect accuracy, or know its energy, okay? So you begin to realize the easiest, my one bit of advice for you as you begin to go down this path is just accept that a lot of the things that you think of as constants in your world are just that, they appear to be that because you are about a meter in size. When you start getting small, you start to see a more granular nature to reality, and we need to do that because the one thing that is certainly the case about nuclei is they are small. And so you need to know something about quantum mechanics. That being said, you're not going to learn an entire huge course on quantum mechanics. We don't have the ability to do that here, the time or the space to do that. So I'm just going to use a few examples that I think are illustrative. They're in Crane, and I've tried to put my own kind of spin on some of these topics. So before we do that, I decided I wanted to offer an extra credit problem. And no, this, you guys do not have to grade this. If you do decide to do this, bring it to me, okay? I won't necessarily be as timely in grading it as they are, but I think it is important because it'll give you a chance to rehearse your skills. This is all up on the web. Go to NUDAT2, and pick one of the following radionuclides and list all of the radiations emitted by it: yttrium-90, palladium-103, or iodine-125. Find a list of radiations produced by it. Determine how much energy would be deposited into a human body per curie of activity. Okay? And I'll say it's due in a week, but you're always welcome to come afterwards and talk to me about it. I just want you to get familiar with playing around with this and figuring out some of this, because as a nuclear engineer, these sorts of calculations are things that you should feel comfortable with. Okay? I don't know how much extra credit it'll be, but it'll be something. Okay, so I do like this video. This was something that Rick recommended, so we're going to go to it right now. It's a YouTube video about the infamous double-slit experiment. Now, what I don't know is how well the sound will transmit to the room. So we're going to have to see if I can get this thing up and running in a reasonable way. Microphone 1. Sorry. There we go. No, that doesn't work. All right, I'm just going to have to play it through here, but let's see how well it goes. Okay. But you know, the truth is, as funky as this may seem to you, really, the role of the observer is central to reality. This isn't a trick. This is really the truth. You measure something and you collapse the wave function. Okay? And the problem here, you may even be willing to accept that, is the whole concept of the wave function. Mm-hmm.
So that, in my mind, it was kind of a little bit aside from showing here's a wave there, here's a particle, and look, it's two particles, this type of thing, as opposed to the concept of the moving charge producing a magnetic field.
So that's true. The moving charge, particularly an accelerating charge, also will produce a magnetic field, but the field does not interfere with itself. When they shoot one electron at a time, the fact that it happens to be creating this magnetic field is sort of irrelevant. Mm-hmm. By the way, you could go and ask the question, what if I shot neutrons through a slit? Okay? Exactly the same thing, no difference whatsoever. The wavelength is different because neutrons have a higher mass. Okay? But that's a good point. There's the magnetism of this is largely irrelevant, although it is interesting since magnetism is special relativity, and now you've got the two most funky concepts together. So that idea that the observer influenced things never sat right with Einstein. So if you're confused and concerned by that, you're in good company. And yet it is true. The convention where we believe that there is an instantaneous collapse of the wave function, and you'll learn what that is in the next couple of lectures, that concept, which we call the Copenhagen Convention, okay, which Niels Bohr was a great fan of, Einstein hated. Okay? The fact that anything can happen instantaneously violated the central precept that he had perceived of the universe, that the speed of light is the absolute speed limit for the transfer of information, and yet the collapse of the wave function does that. And we've done many experiments to exploit this. They fall into this class called EPR, Einstein-Podolsky-Rosen experiments, and it is there. This really happens. The observer collapses things, and the collapse is instantaneous. It's what Einstein called spooky action at a distance. Okay? And I agree, it's spooky. But if you don't accept it and you don't move forward, we can't describe most nuclear behavior. Okay? So when do we need quantum mechanics? Okay? But this is my sort of short answer and example. One example is alpha decay. In short, when we are dealing with phenomena that appear to be energetically forbidden according to classical mechanics, or have charge in the units of E, or size less than or equal to the size of an atom. Okay? When you're in any of these limits, you're over the line. Yes? Mm-hmm. Mm-hmm. This is not a particle. This is a wave function. Okay? The particles themselves have this aspect that if you wish to describe their location or any of their physical properties, you need this wave function. And that wave function you can't ever see. You can only observe actions done to the wave function or the wave function squared, effectively, where the particle is. But that's different. It's like there's a deeper-seated level of reality, this wave function, that we never get to glance directly. We only view it indirectly. And at the moment of measurement, we collapse it. You never see it, you see some other product of it. And you'll see that occur. So hold that thought. I'll point it out later. So here's one example, alpha decay. So in alpha decay, again, I've said this over and over again, sort of the fundamental unit in the nucleus that you could always, if you think of individual units, you could think of protons or neutrons, right? But also alpha particles, because that wonderful pairing interaction. And even in very, very massive systems like uranium or polonium or any of the heavy nuclei, we do indeed have effectively alpha preformation happening inside of the nucleus, and that alpha bounces back and forth inside of the nucleus. I'm representing this here by a potential well. And the alpha needs to get over a Coulomb barrier. Remember, we discussed that early, to get out. Okay? This is a cartoon, by the way. The Coulomb barrier is, everything's rounded in nature. You should be suspicious anytime you have sharp edges. Okay? And where the alpha particle needs to get out, it looks, in this case, the alpha particle is below the Coulomb barrier. How does it get out? It does it quantum mechanically through a process called tunneling. Okay? And this really does work. There's a trick, which I won't be able to go into in this class, called the WKB approximation, where you can calculate precisely alpha decay lifetimes, assuming that you've got a little alpha particle bouncing back and forth in the nucleus between a rigid interior surface and an external Coulomb barrier, and it penetrates. There's a second example, the PP reaction in the sun. This is proton on proton, the fundamental reaction that makes the sun work. Very, very slow, okay? If you look at this, the Coulomb energy required to bring a pair of protons together is just the product of the charges divided by their radii, okay? And that's about a half an MeV. But the sun works, not very well, but enough to keep us happy, okay? And the sun is sitting at 1.5 times 10 to the 7 Kelvin, which is about 2 kilovolts, okay? So something's going on here in order to allow that to happen as well. So if you want to understand quantum mechanics, you have to accept this concept that matter can indeed act like a wave. You just saw Quantum Man with his beard showing you this as we pushed this wave through a pair of slits, okay? Well, what kind of a wave is it? And waves happen in something, right? Well, sort of. Electromagnetic radiation doesn't happen in anything. As hard as we've tried to explore it, there doesn't seem to be any medium, any ether that the photons that are bouncing off of me and traveling to your eyes seem to go through. I could be moving through it fast one way or the other. It doesn't make any impact. So electromagnetic waves are waves in nothing. They're waves in electromagnetism. And matter waves are waves in nothing. They are simply describable using the phenomena of wave dynamics, okay? So de Broglie, and that's how you pronounce this name, de Broglie came up with this very simple relationship between the wavelength of matter and its velocity, okay? It's h over p. So one of the interesting things that happens here is that as p gets small, what happens to the wavelength? It gets big. And in fact, we see this with neutron capture. This is on gold, okay? So this is the capture cross-section again, a concept that we'll be coming back to. It's basically the chances of capturing, okay, as a function of incident energy. And what you see is, in general, they go down. Or as you go to lower energy, which is lower momentum, they go up, okay? So this is a phenomenon that we see over and over again, and nuclear reactors are based on this phenomenon, this concept that the wavelength of the particle increases. The neutron gets bigger, and therefore it can feel around itself in the physical universe and find attractive nuclear potentials to drop into. That's basically what's happening here. What if this were a proton? Well, now there's a problem. The proton has charge. It can't actually even get close. So you instead see this Coulomb effect. Only in the case of neutrons, where you don't have that on top of it, you can see this clearly expressed, this 1 over momentum probability of interaction sphere. So that's the size of the typical nucleus. It's about between 1 and 10 barns, the full size of the nucleus. Okay? And as they slow down, Well, this is where the inner shell is in gold 197. You know, I've said that atoms are about 10 to the minus 10 meters across, but actually, when you start to get to the inner shell electrons in a high Z nucleus like this, the electromagnetic force pulls those electrons in. They get smaller, okay? But even then, they're way up here. So you start to get to this point where the nuclear cross-section actually exceeds the atomic, okay, which is quite an interesting case. But you can do that with neutrons. Okay, so we know this also is proof that something is going on. I can shoot and miss a nucleus by 100,000 nuclear radii, and yet I'll get captured. And how quickly will that happen? So think about this. You've got your nucleus. You're the neutron. You're going along, moseying along 100,000 radii away, and then you drop in. How fast does that happen? Instantaneously. The dropping in is a measurement. And so what you find out actually is that, no, you weren't 100,000 radii away. You were there. You could be anywhere, exactly. Until you do the measurement, you don't know. It's just a probability distribution. But mess it up, you collapse it. I'd say you do wonderful things. I like doing measurements, okay? But you do collapse the wave function. It goes from being a probability distribution, which is really what the wave function is, to being a measurement. Okay? When I'm rolling a dice, I got a probability distribution that I'm going to pair a dice. I got a certain probability of getting something, even the most likely outcome, which is 7, right? I got a 1 in 6 probability. But once I've rolled the dice, I don't have probability anymore. It's done. I've done my measurement. That's the other quote of Einstein's. God does not play dice with the universe. Well, yeah. He does, apparently. She does. It does. Okay? There's this dice playing is fundamental to it. Okay, so the uncertainty principles. This is another central concept in quantum mechanics. So what I like to say is our meter-length concepts of space, energy, and time are inappropriate for small systems. That's really all it comes down to. Okay? You don't have a problem thinking of this. It's like, you don't worry about macroeconomics when you're balancing your checkbook, if you ever do that. Okay? This is just the same thing, okay, except your checkbook's now the quantum universe, okay? You have lots of statistical fluctuations in that. The big thing just does what it wants to do, okay? And there are, generally speaking, the uncertainty principle is stated in terms of 3 forms. The uncertainty in the momentum of a particle times the uncertainty in its position is greater than h bar over 2. The uncertainty in energy times the uncertainty in time, similarly, greater than h bar over 2. Or the uncertainty in angular momentum, J, times the uncertainty in angular location is also greater than or equal to h bar over 2. These two obviously are very similar, okay? The only difference between them is that L equals R cross P, all right? There's the magnitude of h bar. It's important to note that number because this, whenever you're big compared to this number, you got no problem and you don't have to pay attention to the next 3 lectures. Unfortunately, the nucleus is never there, okay? It's 1.05, 10 to the minus 34 joule seconds, or 10 to the minus 16 eV seconds. Okay? There are a couple of important numbers to remember. Okay? If you take h bar and multiply it by c, you get 197.3 MeV Fermi. And if you take that number, flip it over, and do e squared divided by it, this is the fine structure constant. It's 1 over 137, roughly. Okay? These are important numbers to have. If you have them memorized, you're able to do a lot of nuclear physics pretty quickly. These are sort of our acceleration constants for a lot of problems. So one of the nice things about the uncertainty principle is it proves us that our electrons in the nucleus would need to have very high energies. Okay? So one of the early models of the nucleus was that you had, instead of having Z protons and N neutrons, they didn't see the neutron. Neutrons are awful, right? You can't find them. They don't have charge. They don't interact, okay? So instead of that, there was this model that maybe instead what we have is we have 2 Z protons plus 1 Z worth of electrons, okay? And that it adds up to the same charge. So there was a Z worth of electrons in the inside and a Z worth of electrons on the outside. Okay? That was really a model for quite a while. Okay? But you can already see right away that uncertainty would energetically forbid this. Okay? So if I'm inside the nucleus, I'm at 10 to the minus 14 meters, so I've localized the electron within that volume. That means that the uncertainty in momentum that it has to have is h bar over 2 times 10 Fermi. Okay? Well, I can then take that uncertainty in momentum and I can turn it into, using the constants that I just had here from before, the h bar c constant of 197 MeV Fermi, I can turn that into an energy, effectively, of 10 MeV. Okay? So already you know you're sort of in trouble here. Do you know what the rest mass of an electron is? It's 511 keV, or a lot less than even 10 MeV. Okay? And so we go back to what we learned in relativity, that the energy of the particle is just p squared c squared times m squared c to the fourth. We put these numbers in, and it's still about 10 MeV. So the uncertainty principle tells us that our concept of location is imprecise. You're not going to get this energetic particle sitting inside of the nucleus. Okay? Its rest mass even exceeds that. It would be relativistic. Okay, so I said that there are these matter waves. These waves obey rules, yes? Inside of the nucleus? That's a good question. And it's a rather elaborate answer that you'd have to have. By the way, the way this was disproven essentially was through scattering experiments. I'm going to give you that hint. I can't probably get into it in the time that I have, but I want to answer your question. Let me think if I can come up with a quick answer for you. Okay, by the time I lecture next. I don't know if I'll be able to do it quick. If not, I'll just say come to my office hour and we can talk about it. But it's basically through scattering. You're going to see that's one of our big tools that we would show. Okay, so there is an equation Erwin Schrödinger came up with that describes the behavior of matter waves. Remember, we don't observe the waves directly, but we do understand that given the behavior that we can observe, that they exist. Okay? And here's Schrödinger's equation in two different forms. The one on top is what's called the time-independent form, because if you notice, there's no time in that equation. Okay? And it just says minus h bar squared over 2 times mu. Mu is the reduced mass. Okay? Because you may have more than one particle involved, in which case there's actually an average mass between the two. Okay? Times this thing, del squared. Does everybody know what del squared is? Okay, the gradient squared? It's just the spatial derivative times the spatial taken twice, del squared, plus whatever potential energy you have times the wave function equals the energy times the wave function. In general, these sorts of equations are called eigenvalue equations because, think of it this way, you do something to something and you get a number out and the something back. Okay? Differential equation, second order in space. Okay? And this particular function, applying this operator, that first term is just the kinetic energy, the second term is the potential energy. So applying those operators, and you'll see what an operator is in a minute, on the wave function gives you the energy. And psi is the wave function. And really, I think it's reasonable to call this a wave function. So raise your hand if you've had differential equations in this class. Okay? If you have, especially if you've had partial differential equations, then you know that this form of equation that you have, because is the form for a wave equation in time, is what we would use here, is the second order derivative. Okay, actually that should be an x. If I'm doing this as a wave equation, my apologies, that should be an x. So having a second order derivative in space is a wave equation. But there's also a time-dependent version of Schrödinger's equation. And here I have its first order. I have d psi dt times ih bar equals h psi. Okay, where h is this other thing that we had before. It is now the time-dependent, okay, but potentially time-dependent in the case of the potential, composition of both the kinetic energy and the potential energy acting on the wave function. The minute I have a first-order differential equation of this sort, the solution is just exponentials. Okay? We know that. This is just like n equals n0 e to the minus lambda t. The only thing that's a little tricky is that I've got this ih bar in front, so it's imaginary. Okay? But this is the time-dependent picture. And actually, when you have a first-order equation like this, It actually looks a bit more like a heat equation. So this is the tricky part about quantum mechanics. We call it Schrödinger's equation as being like a wave equation, and the solutions are wave-like. But if you look at the time-like behavior of it, it more acts like heat. Okay? So if I start off with a lot of hot in one spot and I let the clock run forward, what happens? Right, it diffuses out. That's what happens here, except the problem here is that it is imaginary. And so if you put an I up in there in the exponential, you start to get this behavior that looks like sines and cosines. There's a nice picture of this. This is a migrating wave packet, a simple one-dimensional migrating wave packet moving through space, okay, a fixed potential. Okay, and this is really what it sort of looks like. It's migrating forward. Okay, so psi is this magic quantity, just to remind you, that I act on. It's the thing called the wave function to get out the energy of the system or the time evolution. Okay? And psi can have both real and imaginary components to it. Okay, so this is a wave that just don't worry about this. Just think of this as math. There's real parts and there's imaginary parts. And one of the things that we identify right away, it's important to do the math of quantum mechanics, is that if you have a wave function psi that has some real part A and an imaginary part B, you can consider another thing called the complex conjugate, where I just flip the sign in front of the imaginary part. That's all. And if I take the complex conjugate of the wave function and I multiply it by the wave function, okay, I will find out where that particle is. That's effectively a measurement of the probability of where the particle could be. And if I want to know if I've got a given particle and I integrate over all x from minus infinity to infinity, I'm going to get 1. We insist on that because I only have one particle. Or as I like to say, I've got to find it somewhere and I've only got to find it once. Okay? So in general, one property that we know for these psi wave functions, they can be complex, they can have real and imaginary components, but one nice thing about all of them is that if I take them and I do this complex conjugate thing and I multiply them, I integrate them from minus infinity to infinity, I'm going to get 1. There's a fancy math term for that. It's called Lebesgue square integrable. Okay? But you don't have to think about that. The important thing is there's certain kinds of functions that you would not expect to find here. Okay? So like a constant. Because if I integrate a constant from minus infinity to infinity, what do I get? Infinity. That's a problem. Okay? All of these things are going to be compact. They're going to live in a narrow space. And if you integrate, you can integrate over past some extent. When you sum them up, they're not going to be there anymore. Okay? That being said, we often cheat, and you're going to see that in quantum mechanics. We forget the behavior. We can do that if we go to a time-independent picture. So in general, how do you solve Schrödinger's equation? The time and space parts of the equation can be factorized. So you've got a component of the solution that's just dependent on where you are and a component that's just dependent on time. And this is another important point. The solutions and their first derivatives are continuous throughout space. Okay? This is in general the limit. So if I look at some particular point in space A, just a place, and I look a little bit to the left and a little bit to the right, and I look at the difference in the wave function, it's going to be 0. Okay? The wave function is not going to do that. Okay? This is one simple thing. Furthermore, if I look at the first derivative of the wave function, again, a little bit to the left and a little bit to the right of some point A, it's going to be continuous. Even the first derivative will. Okay? Second derivative might not be. Okay? And this is an important point to note. Schrödinger's equation, everyone says it's all central. Actually, Schrödinger's equation is pretty simple. It's just waves or probability distributing itself like heat. But the boundary conditions vary from problem to problem. So really, when we say we're solving Schrödinger's equation, you'd think we would be done by now. Because like I think in this chapter in Crane, we do it like 5 times. Okay, it should be solved already. But every time I come up with a new set of boundary conditions, okay, I'm going to change the problem. Even if I stick with the same potential, I'm going to change the problem. So really, this is a fundamental thing, especially when I think about the time-independent Schrödinger equation. In other words, if I give the system long enough to evolve in the right way, it will come up with a solution that depends on the kind of environment that you're in. So if I throw a single particle into this room, close all the doors, get all of us out, the particle bounces around in here. After a short period of time, it's going to come to a set of values, a probability that it can be found at any given point in time. Okay? It's going to come to those values and live there. Okay? It'll take a little while to evolve that, but it will do that. If I then come and move the walls into the room, will it have the same values? No, but it's still obeying Schrödinger's equation, but I've changed the boundary conditions. I've pulled it in closer. So often you'll see this over and over again as we do these different little token examples of quantum mechanics, that I change the boundary conditions in some way, and therefore the solution changes slightly. So let's start with the simplest case. This is a free particle in open space. Okay? So if I'm in open space, do I have any potential? No, I'm just free. I'm free to be anywhere, free to be you and me. There it is. H bar squared over 2 times the mass, del squared psi equals E psi. That's it. Okay? And then this solution is straightforward. It's second order. There's no x's hiding out anywhere. The solution is trig functions. Nice periodic trigonometric functions. Okay? Some component of which is a sine, some component of which is a cosine. Okay? Where I've introduced this concept, this k, this wave number, which is just the square root of 2 times the reduced mass times energy over h bar squared. Okay? So there's another way I can express this. I had a hidden slide in there that just there. Does anybody know about the Euler relation? You can express sines and cosines as being complex exponentials. Okay? So I could also write it out this way. Nothing fancy here. Okay? Now, if I want to add in time dependence, this is the time-independent Schrödinger equation, but I want to put time dependence in, then it's pretty easy because it was just first order in time as well. So now I've got this other component, an omega t. Okay? And that's it. So this is what you get. You end up with a trigonometric function. You end up with a trigonometric function. Okay? And then this time evolution, which is just E over h bar. That's it. What's that?
Time evolution is incorporated simply because in a two-particle open space, they're separable.
That's correct. That's why this can work. We always have this separability between space and time. That's fancy sounding. It just says that what I like to say is this way. The space part, eventually you'll end up in some stable configuration, but it may take you some time to get there. Okay? The stable configuration is Schrödinger's time-independent equation. That's what determines that. And it is basically a bunch of waves. Okay? The time that it would take for you to get there, because it's not like you may be born instantly in a different state, that's the e to the I or minus I omega t. That's sort of the relaxation time for that heat to diffuse out, for the probability to diffuse out into the room and meet the right conditions. Okay? We call that, by the way, that behavior, we call that the propagator in quantum mechanics. As it propagates, it moves you from one point in time to the next. Okay, so I've been using this term operator a great deal. I need to define it. Okay? So an operator is how I get information out of the wave function. So going back to our math, we had this relationship already. If I integrate from minus infinity to infinity of the complex conjugate of psi times psi, what do I get? Always just that alone. Integral of psi star psi. 1. I know the particle is somewhere, but now I'm pulling something faster. I put a little mathematical function in the middle, f. Okay? And f can act. It could have a derivative. It could have an integral. It could have a trigonometric function. It could have these other funky things that I'll be introducing later called spherical harmonics. And it acts on the wave function. And it changes the wave function a bit. Okay? This quantity no longer necessarily has to have units of 1. So what I think of functions as being is they're kind of like factories. Okay? They come in, they take in a raw product of a wave function, and they act on it. And one of these factories creates the momentum. So in other words, I've got this wave function. Now I can find out the momentum associated with the particle by just applying this operator. Okay? How quickly does this happen? Instantaneously. The minute I look for momentum, I find it. It's there. It's there right away. And what I get out is this value, which no longer has a wave function. It's just what we would call an expectation value of what that would be. A different operator might give me energy. In fact, you've seen that. We call it the Hamiltonian. It's the H in Schrödinger's equation. So if I act on the wave function, if I put that H in the middle of the integral, I'll get out the energy. Okay? Another one might give me the angular momentum. In nuclear physics, that's most of the properties. This is the other one that will give you out the parity. And then in some really weird nuclei, there are these other strange quantum numbers that come in, called K, boson seniority, all that stuff. You don't need to worry about this. Okay? It won't be on any exam, but I'd be happy to talk about it. But these are the core things. Because our physical universe, we have conservation of these quantities here uniformly. It's a feature of our universe that we're in, and nuclei have to subscribe to this. Okay? And here's what the operators look like. This is one-dimensional in the x direction. Okay? The operator for momentum is just minus I h bar, take a derivative with respect to x, by dx. Okay? The time one is take a derivative with respect to time. In other words, the momentum extracts sort of a spatial variation, right? The derivative with respect to x is a spatial variation. So that should make some sense. Momentum is sort of a spatial variation, right? Momentum is motion. You're moving. Okay? And energy extracts the temporal variation. Because what does energy allow you to do? It allows you to evolve over time. You move from one state to another. You propagate forward. That's all these operators are. Okay? So, of course, if I put that momentum operator in here, okay, let's look at that momentum one. So now I have to apply a minus I h bar, and I have to take a derivative of psi, and I've got this. Okay? And then if I carry out this, I can associate a quantity with this. So this is sort of a rate at which the wave function is changing with respect to this x direction. And I can associate this other quantity called J, okay, which is simply a probability density. It's a current. It's a flow. It's how fast probability is flowing past a certain point in space. Okay? And so this is in Crane, and it should be intuitively obvious to you what it's just saying. Any time you see like a d psi dx or a d anything dx, it's how fast something is moving through space. It's how it moves through space. And then we have to have this whole flipping of the terms between the complex conjugate and the other function to keep things equal. Okay. If I don't get through all of these things, it's okay. I've padded it into the next lecture. I won't keep you late, I promise. I want to go through and do a first example here. Now we're going to be a little bit, we're going to change the universe a little bit. Instead of being a free particle just moving along, we're going to send a particle in, okay? And it's going to go from one region where it's got a potential well into another region where it doesn't, okay? And so this is how you solve Schrödinger's equation. We know that Schrödinger's equation is the solution everywhere. What do we know about boundaries? They are continuous, right? So we start off with the solution here. We already worked it out before, okay? It's just got this form, complex exponentials. I could have done sines and cosines too. That would have been okay, right? And so in comes my particle. There it is. The solution is there, okay? But it can come in or it can go out, right? It can travel in either direction. And who am I to tell it which direction to travel in? Since both are opposite, this is time independent. In fact, what will happen is that it will come in and it will go out. Okay? Both will happen at some point in time. And this is the time independent picture, so I have to take everything into account. Then we go out here, and now we've got a different energy. Okay? A different term for our energy. But we still have the same form of the solutions, which is a wave. Okay? But I've already cheated a little bit. I've told you that this is a particle coming in from the left and going to the right. Okay? So in other words, the total solution that I have has got one frequency of trigonometric function oscillating wave over here. And then you get here, and the wave function is continuous, at least to the best that I could draw with PowerPoint. And the derivative is continuous, but the second order derivative may not be. And you go from one wavelength to another, because that's all these k numbers are. Okay? That should be k2, sorry. Okay? It just changes the frequency of it. Okay? And again, the boundary conditions here give us this. At that boundary, A plus B has to equal C plus D. Okay? But I've already said here that D is 0. This wave is coming in from the left and it's leaving through the right. It's never going to come back. It's a single pass problem. So I've got these boundary conditions. Okay? I can then recast this in terms of the K numbers. Okay? All this is sitting there in the slide, so don't worry about it. And relate A to B and A to C. And then if I go through and carry out everything, I come up with some quantities, which are the amount of wave that is transmitted through, the amount that makes it over that step, and the amount that's reflected back, just in terms of these K numbers. And what happens? The amount that comes in plus the amount that goes out is 1. I still only have one particle. Okay? And we do this in nuclear physics often. We have what we calculate this thing to be, this transmission coefficient, becomes a recurring theme in nuclear physics. Okay? This could be a particle coming into a barrier like this, or it could be a photon trying to make its way out of the nucleus, or it could be a proton trying to make its way into a nucleus over a Coulomb barrier, or it could be an alpha particle trying to make its way out of the nucleus over a Coulomb barrier. But we have this quantity that we identify called this transmission coefficient. It's basically how much gets through. Okay. All right. Now we have this solution. I actually kind of hate this, but the whole idea here in Crane was to try to give you a picture of what would happen in a cartoon-like fashion. Does nature afford us anything that looks like this, really, in a quantum mechanical way? No, I mean, there's walls, okay? And, yeah, there are walls, finite height walls, and I can run at them, okay? And if I'm too low down, I'm going to bounce off of them almost all the time, okay? So, unfortunately, there's nothing microscopically that looks like this. I mean, if I want to create a potential that changed instantaneously from one value to another, I would rupture space-time. You can't actually do this, okay? Instead, you have nice, smooth things like electrostatic potentials that have 1 over r shapes. Everything is nice and smooth. But it's nice to think about this. I've got my wave function coming in. And here, again, I've got solutions in region 1 and in region 3 that look very similar, okay? They've got this complex exponential form, or you could think of them as sines and cosines. That's fine, okay? The amplitude is different, and the wavelength can be different. But you're always going to have the same general type of solution. In the middle, though, let me come back here, sorry. And in this case, again, we're coming in from the left, so there's no second solution going out. Okay? In the middle, it's actually pretty straightforward as well, because now I have still a solution. I still have to solve Schrödinger's equation, but now I can have this k, this thing that's the argument of the exponential, be imaginary. And then if I do it's imaginary, and I throw it in together with the I that I already had from the outside, I times I is -1. So what you get is a real exponential. And so the probability just drops off, okay? If I was looking at any sort of macroscopic scale, this would drop off so fast. It's dropping off with this sort of characteristic length here. Remember, nuclear lengths are 10 to the minus 14 meters. It would just be gone. You'd never see anything inside there. You'd never get through this. But when you get to a small shape, when you get to a small barrier, like we will often have in a nuclear case, this can actually happen and play a significant role. Okay? So if I then apply my boundary conditions and I say that psi and d psi dx are continuous, I end up with this awful trigonometric, hypertrigonometric form. I hate showing math like this to you guys. It seems slightly damaging. It's in Crane, though, so I feel like I should show it, okay? But once again, I got a transmission coefficient, okay? I've got a barrier height of u0. I've got an energy for the particle coming in. I've got a length for the barrier. These are all the characteristic quantities that you need. And the rest is just how quickly you will transmit, your probability of transmitting and getting through this function. Mm-hmm. There are oscillating solutions on the outside, which is e to the i's or e to the minus i's. In the interior, it's okay to do this because I've done a tricky one on you here. There's actually an I hidden inside of the K. And so when you have the I come out of the K and join the I that's already out there, you get a minus 1. Except, there's an important thing. I had an E minus V0, but I actually flipped this around here because I've got a particle coming in below the barrier, and then there's an I that comes out because I applied a minus 1 on the interior here, and inside I do a minus 1 inside of the square root, and I get an I as it comes out. So this is a trick. It's still what I'm trying to say here. The form is the same, but now this K that's inside in region 2 is a complex K. It's actually an imaginary K. And this only happens in the case that E is less than V0. If E is greater than V0, if this particle was coming in above the barrier, there's no problem. That classically can happen. It just goes over the barrier. This would be that wall is finite in height and I jump over it. Okay? But when you're inside of it like this, this energy term gets a potential taken away from it. Okay? And therefore, when I flip it in this form, I pull out an I. Okay? And now this I is sitting in front of the K. I get this as I alpha. Okay? And this term here becomes a real exponential, not complex. It doesn't look like a trig function any longer. It looks like an e to the minus x. Actually, an e to the minus alpha x. It's just that this one, if I was to redefine this, this is psi 3, this is psi 1, I call this psi 2. Psi 2 has a complex k. It's the middle one right here. That's correct, with a different k than the other ones. Okay? Let's talk about this some more. It's 1 o'clock. Don't worry, we got very close to the end here. Okay? We'll meet again on Tuesday. This takes time. Oh, look, I was one slide from the end. And we'll start with this again. Wednesday.